We hear so much about AI, but have you ever stopped to think about what it really takes to get one of those digital brains out of the cloud and into an actual physical robot? We're not talking about just chatbots here. I mean robots that can actually see, understand, and, do stuff in the real world. So let's dive in. We're going to break down the blueprint for making that happen.
At the heart of all this is a concept called embodied intelligence. And honestly, it's a total game changer. Think about it. It's about giving an AI a physical body. We're talking arms, wheels, sensors, the whole deal. This allows it to actually move around and learn from cause and effect, just like we do. It's how an AI starts to genuinely understand the physical world we all live in. This is that huge leap from just, typing commands to seeing real-world action.
So how do we actually do it? Well, we've got a roadmap. First, we'll look at the robot's nervous system. Then, we need a safe place for it to practice, a virtual playground. After that, we'll build the AI brain itself, and then we'll put it all together so our robot can see, understand, and act. And finally, we'll touch on what's next. Sounds good? Let's get into it.
All right, step one, and this is all about the foundation. I mean, before a robot can even think about doing something smart, all of its parts have to talk to each other, right? They need to communicate, and communicate well. So this is where we build its nervous system.
Okay, so the best way to wrap your head around this is to think of a software framework called ROS2. Just picture it as the robot's central nervous system. It really is this super intricate network that lets the robot's brain talk to everything else. Its sensors, its motors, its grippers, you name it. It's sending and getting signals instantly and reliably. Seriously, without something like this, all you've got is a pile of expensive parts. But with it, now you've got a single, cohesive body. So how does this nervous system actually work under the hood? Well, it's built with a few core components. It has what are called nodes. You can just think of these as individual nerve cells, where each one has a specific job, like, say, processing the camera feed. Then these nodes talk to each other over topics, which are kind of like broadcast channels for messages. And if you need a direct command and response, that's what services are for. The whole thing is designed to be super robust and make sure every single part of the robot is working together in perfect sync.
Okay, so we've got a body, and we've got a nervous system. That's a great start. But how do you teach it anything? You can't just let a multi-million-dollar machine fumble around and break itself on day one, right? No way. So that brings us to step two. We have to create a totally safe place for it to learn, and more importantly, to fail.
And this really gets to the heart of why this step is so critical. I mean, think about it. Trying to test a new robot in the real world is just crazy risky. One little coding bug, and you could have a brand new robot smashing itself into a wall. It's not just expensive and dangerous. It's also incredibly slow. But what if you had a digital twin, a perfect virtual copy? Well, in that world, the robot can try a task 1,000,000 times, fail spectacularly for 999,000 of them, and learn from every single mistake at lightning speed. And the cost? Absolutely zero.
Right, so it's super important to understand that this digital twin, it's not just some video game. Not at all. We're talking about a super high-fidelity simulation that perfectly mirrors the real world, and it's constantly syncing data between the virtual robot and the physical one. It's literally the ultimate practice ground. It lets developers test and tweak and perfect every single move the robot makes in a totally safe sandbox. All right, let's get to step 3. We've got the body, we've got the safe training gym. So what's missing? The mind, of course. It's finally time to build the AI brain.
So, if we're sticking with our analogy and ROS2 is the nervous system, then a toolkit like NVIDIA Isaac, well, that's the cerebral cortex. This is where all the heavy lifting of actual intelligence happens. It's what provides those super powerful AI algorithms for things like perception and navigation, the stuff that turns our robot from just a dumb machine into a truly autonomous system.
So what does this brain actually do? Well, first, it handles AI perception. This is huge. It's how the robot can tell the difference between, say, a coffee mug and a water bottle. It also powers navigation, so the robot can map out a room and zip around without bumping into everything. And this is the key. It plugs right into our digital twin for training, and it uses hardware acceleration to make all of this processing happen ridiculously fast.
And that brings us to step 4, which is really the grand finale. This is the big integration step. It's where we take the nervous system, all that virtual training, and that powerful AI brain, and we put them all together. This is the moment we create a robot that can finally go out and do complex things in the real world.
And it really all boils down to this simple but incredibly powerful loop: vision, language, action. So first, the robot uses its cameras to perceive what's around it. Then, it uses language models to understand what you told it to do, like if you said, "Hey, bring me that blue box." And finally, it combines what it sees with what it understands to actually perform the physical action. That right there, that's embodied intelligence in action.
So, there you have it. With that final piece in place, we've basically gone from a box of parts to a fully functional, intelligent robot. It's pretty amazing. So, let's just take a second to recap and put all the pieces of this blueprint together.
Okay, so this whole blueprint we've just walked through, it all comes down to these 4 pillars working together perfectly. You absolutely need that reliable nervous system to connect everything. You need that safe digital practice ground so it can learn without breaking things. You need that powerful AI brain to make sense of the world. And finally, you need to tie it all together into a cohesive identity so the robot can see, understand, and act. That is the recipe. That's how we build the next generation of robots.
And you know, that really brings us to the biggest question of all. This stuff, it isn't science fiction anymore. The blueprint is here, it's clear, and people are using it right now to build more and more capable machines every single day. So the real question for all of us is, now that we know how to do this, what are we going to build? What amazing problems are we going to solve with this incredible new power?